We'll now discuss the basics of lighting and shading. This is really the key part of this lecture, where we discuss the different shading models used and we discuss the different types of light sources used. Putting this all together, you can understand how lighting and shading works in computer graphics and in OpenGL, and begin to start working on homework 2. The motivation for a lot of this is what happens physically in the real world. And although this lecture will discuss the concepts intuitively, it's also possible to formalize them based on physical arguments. In the real world, complex materials and lighting interact. So the shading you get out of an object, what it looks like, depends on the interaction of the illumination in the scene and the material properties of which that object is made. For now, we're just going to talk about some very basic approximations, just like we did Garot in Phong shading, similarly in lighting models, to capture the key effects, the overall color of an object, as well as the specular highlights. This lecture is largely inspired by the old OpenGL fixed function pipeline and largely reproduces the shading that would be reproduced in that pipeline. Of course, that pipeline is not physically based, it's a number of approximations. And of course, today you have the ability to write arbitrary shaders. So one of the things to think about after this course is ways in which you could improve on the shading model, potentially make it nicer, make it more physically based. Let's start with the types of light sources in the scene. And the first light source is a very simple one, is a point light source. Of course, in the real world, there's no such thing as a point light source, but many practical lamps can be idealized as point lights. Being a point, it has a position in space and it has a particular color. That's all you specify. So the position is a 4-vector in homogeneous coordinates and the color is again RGBA. Point light sources come with this attenuation or quadratic model. We'll describe what this is and how to set the parameters for KC, KL, and KQ. First, let's consider the case when you have a point light source and it is emitting light. How much light will be received here versus here? This is given by the standard inverse square fall-off in physics, where you take this distance, r, and the intensity is proportional to 1 over r squared. This of course holds in 3 dimensions. In flatland it would be somewhat different, but in practice in our world this is a standard law. It's true for light, electromagnetic energy, it's true for gravitation. Essentially you can think about the same amount of energy being on a sphere surface of radius r. The surface area goes as r squared, and so the energy decreases. So this is a very standard argument where d is the distance to the light source. It applies here, and it would argue that one should set kq is equal to 1 and the other components equal to 0. However, let's consider some other types of light sources. So let's consider a line light source, something like this, a cylinder, a tube light that's emitting light. Of course, you might wonder, why are we considering this line light source instead of a point when we said we're talking about point light sources? Why don't we have a separate primitive in OpenGL that deals with line light sources? The reason for that is that a point light source is easy to shade because at each location on the surface, you just need to look up where the point light is coming from. Whereas for a line, you really have to add up or do an integral over the entire line. And so it's very common in OpenGL that you might draw the geometry of a tube light, but for shading purposes, you will concentrate it as a point source at the center. However, the attenuation for a line source is different, and you can go through the mathematics, you can go through the integration, and essentially the intensity falls off as 1 over the radius. So if this is the radius, the intensity will fall off as 1 over the radius. And that's where this term KL comes from. And so you would really want, in this case, to have KL is equal to 1. And of course, this is assuming the light source itself is infinite. So the viewer is a certain distance away from it, which is small compared to the light source width. Of course, if you're far away from the light source width, eventually it behaves like a point light source. And so that would argue that you have this linear attenuation. And in other cases, such as when you have a light source that's far away, or we handle that separately with the directional source, but instead of a line, supposing it's actually an area source, something like this, and one is close to the light source. So in that case, it becomes harder to compute what the attenuation is, and very often you may just want to keep it with the constant attenuation. So an example of this is what is the illumination you get from a wall. And one of the things you talk about when you talk about radiance computations is that the wall looks similar from a range of different distances on it. And so in cases like this, you want to keep the attenuation constant. In practice, many people, when they're doing computer graphics, just ignore this attenuation, set kc equal to 1. And in fact, in our assignments, that's what we'll be doing, right? So we'll be representing the attenuation very often as 1, 0, and 0. Even though for a real point light source, you have quadratic attenuation. And so in OpenGL, we're given the option of using the appropriate attenuation model that is appropriate to your light source. Finally, you can have a directional source, and you can include that within the point source simply by setting the homogeneous coordinate equal to 0. So if W is equal to 0, the source is really at infinity. And that's a good model for something like sun, or even you have a light source which is very distant relative to the scene. Of course, if the light source is a directional source, the question of distance doesn't really come into play, and there should be no attenuation. In fact, the KL and KQ terms should be equal to 0. That's as far as the lighting is concerned. The next thing we need to talk about is the material properties. This is, how does a surface reflect light? For that, we need to know the surface normals. So far, we had one brief segment on transforming normals, but mostly you consider the points or geometry of the surface and you're moving them around to different locations. However, for lighting calculations, it's absolutely critical that you know the surface orientation or the surface normal. And that affects the diffuse reflection, the specular reflection. It affects the reflected direction of the light source. You often want to find the reflected direction. The standard way of doing that is to specify the normal at each vertex and then interpolate it to each fragment. In some cases, for procedural models, you might have an analytic formula for the normal at each point, such as on a sphere. For objects such as teapots, spheres, etc. that you specify with GLUT, GLUT does it automatically for you. And so you might wonder how the teapot in all of my assignments actually has normals correctly for lighting. The answer is GLUT does it for you. For parametric surfaces, you can do it manually. And in fact, there are some GLUT evaluators to do it for spline curves. For more complex shapes, there's actually an interesting trick in which you can average the face normals to get a vertex normal, and I'll show it to you in a moment. So let's assume you have a surface, something like this. You have triangle 1, you have triangle 2. Now I want to get the normal at some vertex, let's say this vertex, and so I can complete that I have a few more triangles, let's say. So I want the normal here. What I do is I consider the normals at these locations, and these are what are known as face normals. I average all of them together, and you can use a weighted average in order to get what's known as the vertex normal here. Then to get a normal anywhere interior, I interpolate the vertex normals. And so that's a standard technique of averaging the face normals for more complex shapes. Let's talk about the different shading modes. There are 4 basic things that we will consider: ambient, diffuse, specular, and emissive. Let's first consider the emissive term. Emission really corresponds to things like sunlight, things like light sources, and it really corresponds to emission from them only when you're looking directly at the light source. So not when you're looking at its reflection on something else. The reason for that is if you look directly at the light source, even if there's no light from elsewhere falling on the source, it's going to emit light in your direction. In OpenGL, there is a little bit of a gotcha that to actually see a light source, it's not enough to create it, you must create geometry. So only geometry is what you see. Geometry is lit by light sources, but you don't see the light sources, you don't see the camera. So what I would do is I would create a rectangle. I mean, it's not a point because I have to see it, for the light source. And I would give it an emissive property, let's say of white, so that it always appears white. That's a very common way to set things up. This is not relevant for surfaces that are not emitting light. The second thing is the ambient term. And the intuition there is that even if there's no light falling directly on the surface, there is light that's bouncing about in a room and gives it a general diffuse or ambient feeling. So if you go into a room, this would be light cast typically by large light sources, light that's bouncing off the wall, and so on. It's really a hack because it is possible to simulate the exact distribution of light in a scene. This is a very rich research area in computer graphics rendering known as global illumination. We'll have one lecture at the end of this course talking about a development there known as the rendering equation. But ambient illumination is a simple hack which says light is bouncing around the scene many times. Eventually its distribution is approximately uniform, coming equally from all directions. So let's just give the scene a global constant. And the advantage of that also is that I will actually be able to see my computer graphics image. I never have black pixels. And so you just give an ambient intensity to the whole scene. Typically this is very low, something like 0.1 or 0.2. The next aspect is the diffuse term, which corresponds to rough matte surfaces. So something like the walls, which are rough and matte, something like the floor if it's not polished. Faces are to a certain extent matte. Of course, they have much more interesting reflectance properties. And this is something which technically we refer to as Lambertian surfaces in computer graphics after Lambert. The idea is that light reflects equally in all directions. Of course, in practice, no surface will reflect light equally in all directions. The closest to this is a material known as spectralon, but even it has a fall-off. However, it's a good idealized model in computer graphics that light hits a surface and then is equally reflected in all directions. So the surface is not smooth and polished like a mirror, it's a rough surface, and therefore the reflection comes about in any direction equally. One of the key aspects of this is the cosine fall-off. So n dot L is just the cosine of this angle. So if you let this be the incident angle, this is just equal to cosine of theta n. And in fact, we have to technically take a max of this and 0 because you don't get light from below the surface. And this is because you see that the light is coming in here, so it's really incident on a plane here, whereas the light that's flowing normal to the surface is attenuated by this cosine factor. It's very important. It's what gives rise to season, because the sun's light is at an oblique angle in the winter, it's at a more normal angle in the summer. And we can write down the formula like this. So you sum over all of the light sources in the scene. You look at the intensity of the light source times the diffuse component of the material times the attenuation for that light source times the max of this cosine term, or L dot n, and 0. That's what the diffuse or the Lambertian term is. Next we come to specular reflections. We've already had a lot of talk about the Phong illumination and shading models. The specular reflections corresponds to glossy objects. We said glossy paints, whiteboards, things like that. And even if you look at the typical plastics or metals, you will have some reflection. The idea is that light reflects in the mirror direction. So all of you in school have studied this law of light reflection. The incident and reflected directions and the normal lie in the same plane, and the angle of incidence is equal to the angle of reflection. So this is the incident angle, this is the reflected angle. So let's say theta incident, theta reflected, and they have to be equal. But the eye is not actually in the reflected direction, so it's really the rough reflection. If it were a smooth mirror, you would get intensity only here, no intensity here. And so you can see that how far off angle the eye is will actually affect the amount of light that's reflected. So here is the reflection lobe. You can see that light is reflected mainly in the mirror direction, but there is some intensity that goes towards the eye. Let me repeat my slide about the Phong illumination model, which covers specular or glossy materials. And really, you can be considered to be blurred reflections of the light source. As you increase the roughness, you get a greater blur in terms of the reflection of the light source. So let's go back and talk about Phong illumination. Despite its long history, this was first proposed in the mid-1970s, and even though we now know that there are more accurate physically based ways of doing reflection, it's still a very commonly used model. And Fong's idea was generally that he wanted a simple way to handle view-dependent highlights, not necessarily physically based. And so he said, we're taking the dot product for diffuse surfaces. Why don't we take a dot product for specular surfaces, but instead of taking the normal and the lighting direction, we'll take the eye and the reflection of the lighting direction about the normal. And furthermore, we'll raise the cosine to some power so you can control how shiny the surface is, how wide the highlight is. There's an alternative form which just says take the half angle between the light source and the viewer and take the dot product of that with the normal. So then it's much closer to standard diffuse illumination, which is the dot product of light and normal. This is the dot product of the half angle and normal. And again, you can raise it to some power. That's something that's known as the Blinn-Phong model. And actually, for physical surfaces, the half angle form is more accurate. It's the form in standard OpenGL and largely what I asked you to implement. Let's first consider the standard Phong formula, not the Blinn-Phong form, where you're considering the reflection of the light direction about the normal, that is, the angles are the same and it's in a plane. That's why I can draw this diagram on a plane. And now I'm looking at really the angle between the reflected direction and the eye. This is between the reflected direction and the eye. And that angle, that cosine, I'm going to now raise to some power. Okay? So the question is, I just need to find the mathematical formula for the reflected direction. And it's relatively easy to do it, although the formula is somewhat complex. So we first look at the lighting direction. And I'm going to break this into the horizontal and the vertical component. So the vertical component is along the direction of the normal. The horizontal component is going along the surface. Now the horizontal component doesn't actually change for the reflection, but the vertical component, the direction is changed. And that's essentially what a reflection is. So you can take the original lighting, which includes the parallel and the perpendicular component, and what we want to do is flip this component along the normal. So you consider the component along the normal, and you take twice that in order to flip it, and you subtract. So essentially what we have is we have the lighting. Then what you want to do is subtract out this component. So that will be the dot product of the lighting and the normal along the direction of the normal, assuming all of these things are unit vectors, and you want to have a factor of 2 in there. So I've just inverted the signs in order to make this work out and get the correct sign. But essentially that's what you have. You have 2 of L dot n times n, because that corresponds to the reflection, and then you subtract out the lighting. An alternative form is the half angle form, which is the Blinn-Phong formula, and that's after Jim Blinn, who was one of the pioneers in computer graphics. Just tweak this formula a little bit, and there you just take the lighting and the reflected direction, you take half angle between them. So you can look at h. If these were scalars, would just be L plus R divided by 2. In our case, you can write it as L plus R, and you can normalize by the norm of L plus R. So what is the final specular reflection formula? You have some intensity for the light eye times the specular coefficient of the material times the attenuation times, again, max of n dot h comma 0, just as you had max of n dot L comma 0. But there is this additional shininess term which controls how sharp the lobe is. So if shininess is very large, it's concentrated about the half angle direction or the mirror direction. If shininess is 0, then it essentially is very similar to the Lambertian case, except using the half angle instead of the lighting direction for the cosine. Okay, so let's do one example of this. Let's go through the MITES 3 example. And here is my program. Okay, Now what I want to do is change the intensity. So let's look at this and let me bring in my editor. So first of all, I'm going to make the teapot move a little bit faster. So I'll change this to 0.005. And then I want to change the intensity, the highlight. So right now the exponent is 100. Let's make the exponent equal to 10. Okay, so remember how the highlight looked like earlier. I'm going to show you writing actual code. So I come here and I say make my test 3, and it goes through the compilation and eventually it will make the program, right? So now all I need to do is run it, and you notice that the highlights are much larger. So let me make it the same size as the earlier, this one. And you'll notice that if you compare the highlights on this teapot here, which was my original program, to the highlights here, you'll see that the highlights have now become much larger. And of course my teapot is moving somewhat more quickly because I made it move, I changed the increment. And so if I made the highlight back to 100, then I would get this. So this is with 10, this is with 100. And in this way you can shape the way in which the highlights look. In the next segment, we'll be talking about the fragment shaders and ways in which you will actually implement this in OpenGL.